topic that we are going to discuss, the next part of the second unit is time varying fields. Okay, so we will be discussing time varying fields and Maxwell's equations. Okay, so what is a time varying field? Just before that, okay, so in the first unit we have studied with charges at rest. Okay, charges at rest. That means whenever a particle, charge particle is static, we have seen that there will be some force generated. Okay, we have seen that the force will be generated. Okay, this force is just a function of space. Okay, this force is just a function of space. Okay, and it is independent of time. That means the value of the force will remain constant at all time instants. Correct? So this is the first point. Second thing is, whenever the charges are moving with constant velocity, whenever the charge is moving with constant velocity, that means whenever I apply DC current, okay, DC current through the conductor, in these cases the force that is developed will also have magnetic nature, but it is also static with the time. That means it does not vary with the time. Okay, so here also it is static with the time. This is also static with time. That is, it does not vary with time. Okay, now the third thing that we are discussing is whenever the charges are moving with acceleration. Okay, whenever the charge particles are moving with acceleration, that is, okay, the current that we are applying, is AC current, or we are making such that the current I varies with the time. Okay, so we are producing time varying currents. Okay, so if the current if a time varying current is passed through a conductor, okay, if a time varying current is passed through conductor, then what we get is, we will also get a force, and this force will be having is dependent on time and space. It is a function of time and space. Okay, and at the same time the force that is developed will have both electric and magnetic nature. Okay, so this force, whatever that you develop, okay, because of the time varying current, it will have both electric nature and magnetic nature. Okay, so okay, so whenever I apply time varying currents, whenever we get time varying currents, what we observe is the force that is developed, the force that is produced, is both a variable of time and space. Okay, first point, it is a variable of time and it is variable of space. Second point is, this force whatever that you develop has both electrical and magnetic nature. Okay, so electrical nature will be there and magnetic nature will be there. Okay, so such a type of forces or such type of fields, so which has both electrical and magnetic nature, are called as EM fields, electromagnetic fields. Okay, so electromagnetic fields, okay, and the field will be called as time varying fields, and the field will be called as time varying fields. Okay, so how this time varying fields, that means we should this time varying fields, it should have both electrical nature and magnetic nature. How is that? We will see with the help of Faraday's laws. Okay, so is this point clear? Whenever we have time varying currents, or whenever we have charges moving with acceleration, whenever the charge particles move with acceleration, we get time varying fields or time varying forces. Okay, this time varying forces are a function of both space and time. Okay, that's the first point. Second thing, this field whatever is produced, it will have both electric nature and magnetic nature. Hence we call them as electromagnetic fields. Okay, so whenever the charges are moving with acceleration, we get electromagnetic fields. Okay, electromagnetic fields. Okay, electromagnetic field means the force or the field, the region. Field is basically region, correct? So field is basically region, okay, so region where the force is felt. Now what is EM field or EM thing? So here, any particle that you put, it will experience both electric field, okay, right, as well as magnetic field. Okay, the force that you produce, that will have both the electric nature and magnetic nature. Okay, magnetic nature, we know it will attract the particles that are of magnetic materials. Similarly, electric nature, right, it will induce some charge into the material, or potential into the material. Okay, so it will make the charges to move, right? So any particle that is present inside this kind of fields will have both electrical nature and magnetic nature. Okay, so electrical nature will be present, magnetic nature will be present. So we will get electromagnetic fields whenever we move a charged particle, right, with acceleration. Okay, right? Is this point understood? Right? Okay, so this thing, right? Now, to prove this, right, we have a simple law called as Faraday's law. Faraday is the first man who has demonstrated the presence of electromagnetic fields. Later, Hertz, right? We know the unit of frequency is Hertz, right? Hertz is a scientist, so he has demonstrated the presence of wave nature to this field. Okay, so what is that, we will discuss in the third unit. So as of now, we will discuss how these electromagnetic fields are generated, right? So the electromagnetic waves or electromagnetic signals fields are demonstrated by Faraday. Okay, so Faraday said that the electromagnetic waves, okay, or the time varying fields, they can be produced in two ways, right? There are two ways by which you can produce, right, electromagnetic waves. Okay, so the two ways are the electromagnetic fields can be produced with the help of two ways. Yeah, just a second. Okay, so first method is, right, the first way of producing an electromagnetic field, EM field, is, right, we need to get time varying current, right? When will we get EM wave, EM field? Basically when we have a time varying current. Okay, so one method is simple. So this method is simple. What we do is we will have a time varying current applied to or passing through a conductor. Okay, the current I that I take is an AC current. Okay, so the current I take, AC current, right? So AC current, this AC current, right, because it is changing with the time, so it will produce, right, it will produce, because the charges are moving, right, it will produce a time varying magnetic field. Okay, so this will produce a time varying magnetic field. And if I have, right, any closed loop, right, any closed loop in the proximity of this, then this time varying magnetic field, right, this time varying magnetic field, it will link up, right, or this time varying magnetic field, right, when it is associated with the coil, right, with a constant coil, it will generate a time varying electric field. Okay, so time varying electric field will be produced, right? And this time varying electric field, when combined with the magnetic field, we will get electromagnetic field, EM field. Okay, right? So the first method for producing EM field using Faraday's law, what Faraday has said is, right, so there are two ways of generating EM fields. EM fields means electromagnetic fields having both electric nature and magnetic nature. Okay, so the first method is this. What is this first method? Here what we do is we apply time varying currents through a conductor. Okay, AC current is applied through the conductor. So this will produce, right, this AC current will produce a time varying magnetic field. Okay, magnetic field B bar, right? Earlier it was constant with the time. Okay, earlier it was constant with the time. Now it is changing with the time. So B bar is changing with the time. So we will produce a B bar which is changing with the time. Okay, so because of this B bar, we will get electric field induced into the coil or conductor that is placed near to it. Okay, EMF will be generated. So this EMF will, right, this potential, right, because of this potential, we will get electric field, which is also time varying in nature. Okay, which is also time varying in nature, because the field that is producing is time varying. Okay, So because of this, we will get one type of fields, EM fields, right? EM fields. Okay. So electromagnetic fields around this entire setup, right? Around this entire setup, we will get electromagnetic fields, right? Okay, electromagnetic fields that are right, time varying in nature. Clear with this, right? Okay, so this is one way, right? Okay, this is one way. This is called as motor action, right? So this is called as the motor action of the generation, right? EM wave generation. Okay, so the second method is the generator action, right? So generator action, what we do here is, right? So generator action or the Lorentz equation, yesterday whatever I discussed, right? So here what we do is, okay, yeah. So here what we have is, so we have, for example, a DC current applied to a current carrying conductor. Okay. So DC current is applied to a current carrying conductor, right? So we have studied that whenever we apply DC current through a current carrying conductor, right, I will get magnetic field. Correct? Okay, this magnetic field is static in nature. So it is static magnetic field. Okay, it is not time varying, it is static magnetic field, right? Now, if this static magnetic field is induced into a coil, right, into a coil which is rotated, right, which is rotated with a velocity. Okay, so that is, the coil is moving, right? So yesterday we studied the Lorentz equation where we studied that F bar is equal to, right, what is F bar? F bar is equal to, right, Q into, okay, V bar cross B bar. Okay, so B bar is constant. B bar that you produce is constant. It is static magnetic field. Now this static magnetic field is linked to a moving charge, right? The charge or the conductor is here is moving. So whenever I do that, the force that I produce will be right. Okay, the force or the force that will be induced, right, will be, okay, time varying, right? It will produce a time varying force, right? Varies with the time because the particle is moving, right? So because of this, F bar by Q bar is nothing but E bar. Okay, so electric field will be generated if the coil is designed in such a way, okay, if the coil is designed in such a way that it moves with accelerating velocity. Okay, so I am moving the coil with not with a constant velocity but with velocity, right, with the accelerating velocity. Okay, if V bar the velocity varies with the time, right, if it is moved with right, different velocities at different time instants, then what I get is, I will get the force which is time varying in nature, right? This force, right, will be electrical nature, and that will cause electromagnetic waves or EM fields to generate. Okay, right, that will produce, right, EM fields, electromagnetic fields, which are time varying in nature. Okay, so right, this way of producing electromagnetic waves is called as generator method, generator action. The all the, right, as I told you, the generators, the current generators, everything, they use this concept. Okay, right? So quick recap, right? Quickly, what let us come back to what we discussed, right? So firstly, the first point that we need to understand is, whenever there is a charge with acceleration, right, whenever the charge particle is moving with varying velocity, we will get fields or forces that are, right, varying with the time. Okay, so such type of time varying forces or fields will have both electric nature and magnetic nature. Okay, right, electric nature and magnetic nature. So these fields are called as electromagnetic fields. Correct, this point is clear. Okay, so whenever charge particles moves with acceleration, we will get electromagnetic fields, right? Now how to generate, that means the charges should move with acceleration, correct? So that means we need to produce time varying currents, okay, or time varying fields. So for producing time varying fields, Faraday has given us two methods. Faraday is the one who has discovered electromagnetic fields, correct? So he has given two methods, right? What are the two methods? One is called as the motor method of generation, other is the generator method of generation. Okay, so first method, if I observe, in this method, what I do is, right, everything is static here. Nothing is moving. Okay. Both the coil that is producing the current is static, and as well as the, right, the coil that is producing the electric field is also constant. Nothing is moving. Only thing is we are applying AC currents. Okay. AC currents and three phase currents, AC currents, alternating currents that vary with the time. So we apply AC currents, right? This AC current will produce a time varying magnetic field. Okay. And this time varying magnetic field will link to, right, will magnet, whenever links to a coil, it will produce EMF, right? That EMF will give us a time varying electric field. Okay. So in this way, we generate electromagnetic wave or electromagnetic field, which is time varying in nature. Okay. So this is one way. Second way is using the Lorentz concept or using the generator concept. Here what we do is, we will apply DC current itself. We will apply DC current to the coil, right? And the coil is static. Okay. The coil is, the conductor is static. The current carrying conductor is static. Okay. So it will produce a static magnetic field, right? Now this magnetic field is linked to a coil which is rotated around the conductor, right? So what I am doing is, now I am right, applying, I am moving the coil right around the conductor like this. It is rotating like this. Okay. The coil is rotating like this, and that too, the rotation is not constant with the time. It is varying with the time. The velocity of the rotation varies with the time. So because of this, what happens is, we will get time varying fields. Okay. So these are the two methods by which we can generate electromagnetic fields. Okay. So these are called as Faraday's experiments, right? So Faraday has Faraday's law, right? Faraday has said that whenever you vary with the time, we will get, right, an EMF. Okay. An EMF will be produced, right? And that EMF will be, right, okay, time varying in nature. Clear with this? Any points, any doubts in this? Right, quickly. Let us go to the continuation. So these are the two ways by which we can generate electromagnetic waves. Okay. So one method is to generate using this concept. The other is to use this concept. Okay. Now what is the next thing is, so Faraday's law, mathematical representation of the Faraday's law, right? So we can represent the Faraday's law mathematically. So what Faraday has said that right, whenever there is a time varying current, or whenever there is a, right, time varying field that is produced, an EMF will be generated, and this EMF basically will be proportional to the flux that is producing the, right, the rate of change of the flux, right, induced in the conductor. Okay. So, right, the mathematical representation of Faraday's law is this, right? So what Faraday's law says is, so either use the first method or second method, right? Whenever we get time varying currents, right, we will produce a time varying field. This time varying field will induce some EMF, okay, into the coil, right? Some EMF into the coil, or some voltage potential is developed in the coil. Okay. That potential is directly proportional to the flux that is producing, or that is flux produced, or magnetic flux produced by the, right, conductor. Okay. So E is directly proportional to N d phi by dt. Or to remove the proportionality constant, what we introduce is, we introduce a constant called as N, where N is basically number of turns in the coil, right? Number of turns in the coil. Okay. So we have, so E is equal to N d phi by dt, right? So, right, the definition of Faraday's law is, the EMF produced by a time varying field will be proportional to the rate of change of the flux in the conductor. Okay. The rate of change of the flux in the conductor. So he has given this expression mathematically, right? And okay, so what we get is E is equal to, right, N d phi by dt, where N is the number of turns in the coil, right? And to add to this, what Lenz has said that, right, the Lenz, right, Lenz law we might have studied, right? So what Lenz has said that whatever the EMF that is produced in this case, right, EMF produced in this case, it will be opposite in direction to the flux producing it. Okay, so he has added a sign convention, okay, sign to this. Okay, so he said that the EMF that is produced will be opposite to the flux, okay, that is producing the EMF. So E is equal to minus N d phi by dt, right? Clear? If N is equal to 1, if the number of turns is equal to 1, then what we get is E is equal to minus d phi by dt, correct? E is equal to minus d phi by dt. So this is mathematical representation of Faraday's law. Okay, Nama? Right? So, okay, mathematical representation of Faraday's law is this thing, right? EMF is equal to minus d phi by dt. So the EMF produced will be equal to minus d phi by dt. Okay, so right, so this is all about Faraday's law.